Hi. In this session, we're going to have a few more problems in which we calculate inverse Laplace transforms using some different methods. So let's start with a simple problem in which we calculate the inverse Laplace transform of log s plus a divided by s plus b. And remember, so far we don't have any function for which the Laplace transform is logarithm of something. So anyhow, we rewrite this as the inverse Laplace transform of log of s plus a minus log of s plus b. Log a by b is equal to log a minus log b. Now let's consider f of s is equal to log of s plus a minus log of s plus b. Now, let's consider the first derivative of f of s, which is equal to the first derivative of f of s is equal to 1 by s plus a minus 1 by s plus b. Now we have some functions 1 by s plus a and 1 by s plus b, some functions for which the Laplace transforms are known. So the inverse Laplace transforms of the derivative is known. So let's consider minus of d by ds of f of s, which is equal to 1 by s plus b minus 1 by s plus a. Now we have a result which says that Laplace transform of t into f of t is equal to minus d by ds of f of s. And we can this particular result can be used to find the inverse Laplace transform. So the inverse Laplace transform of minus d by ds of f of s equal to the inverse Laplace transform of 1 by s plus b minus 1 by s plus a is equal to t into f of t, where this f of t is the uh, inverse Laplace transform of capital F of s. And this gives uh, inverse Laplace transform of 1 by s plus b is equal to e raised to minus bt, then minus e raised to minus at is equal to t into f of t. And what we are looking for is the value of f of t, and f of t is e raised to minus bt minus e raised to minus at divided by t. So this is how we can find the inverse Laplace transform of uh, logarithm of s plus a divided by s plus b using a simple trick. And now let us have another function. Calculate the inverse Laplace transform of 1 by s into s square plus a square. And here what we are going to use is the result which says that integral 0 to t f of t dt is equal to 1 by s into f of s. Laplace transform of integral is 1 by s into f of s. So if we take the inverse Laplace transforms on here this Laplace transform of this. If we take the inverse Laplace transforms, then inverse Laplace transform of f of s by s is integral 0 to t f of t dt. For this, we can replace this t in the integral with some other demi variable. Okay, anyhow, here we have the Laplace inverse of 1 by s square plus a square, which is nothing but uh, 1 by a sine 8. So uh, if you divide the Laplace transform of sine 80 by s, then the required inverse Laplace transform of um, 1 by s into s square plus a square is equal to integral 0 to t 1 by a sine a t dt, or let's have some other demi variable a u d. Now this is equal to 1 by is a constant is taken outside, then sine a u, the integral is minus cos a u divided by a in between the limit 0 and t, which is equal to 1 by a square into the upper bound is minus cos a into t, and the lower bound is cos 0 is 1. So this is the limit, and this is equal to uh, 1 minus cos a t divided by a square. So that's again another trick by which we find the inverse Laplace transform of function. Now let's solve another uh, problem in which we use the theorem or result Laplace transform of f of t divided by t is equal to integral s to infinity f of s ds. And the problem is find the inverse Laplace transform of s plus 3 divided by s square plus 6s plus 13 the whole square. Okay, anyway, we can find try the methods of partial fractions. All those kind of methods can be tried, but here we have a uh, uh, simple method. We take f of s as s plus 3 divided by s square plus 6s plus 13 the whole square. Now, um, since if we replace the denominator with a u, then the numerator is somewhat like du. So that kind of a relationship is here, and that is why we use the Laplace transform of derivatives to have the result. Okay, so what we have is integral s to infinity f of s ds. Its inverse Laplace transform is f of t by t. So first we calculate integral s to infinity f of s ds. Integral s to infinity f of s, that is s plus 3 divided by s square plus 6s plus 13 the whole square ds is equal to, now to integrate it, um, the denominator is taken as u s square plus 6x plus 3 is equal to u. So 2s plus 6 is equal to x plus 6 ds is equal to du, or s plus 3 ds is equal to 1 by 2 du. So it is u square into, here it become 1 by 2 du, and it varies from s to infinity. So okay, let us keep this as here because we can change the variable after integration. So it is integral uh, 1 by u square. The integral with respect to u. 1 by 2 is taken outside. Then it is 1 by u and so minus n also in between uh, s and infinity. It's equal to 1 by 2 into minus 1 by can replace u with its value, that is s square plus 6s plus 13, that's the value of u in between s and infinity. So obviously at infinity it is 1 by infinity, which is 0, and at the lower bound uh, it become 1 by 2 into 1 by s square plus 6s plus 30. Now that is the integral. Then if we take uh, L inverse on both sides, we have L inverse of 1 by 2 into 1 by s square plus 6s plus 13, which is integral s to infinity f of s ds is equal to f of t divided by t, and this will give uh, the Laplace. Okay, now we have to find the Laplace inverse of left hand side. um, 1 by 2 is a constant taken outside. Then what about the Laplace inverse of this thing? So for that we rewrite it as a perfect square. For that, mm, so a square plus 6x plus uh, 13. So the it is a square plus 6s. Now the half of 6, that is 3. 3 square is added and minus, then plus 13, which is equal to 1 by 2 into L inverse of 1 by s square plus 6s plus 9 is a perfect square, that is s plus 3 the whole square. Then what remains is minus 9 plus 13, that is plus 4. Now this is a form for which we can have the Laplace transform or Laplace inverse transform. 1 by s square plus a square is Laplace. Okay, it's the inverse Laplace transform, the Laplace transform of the form sine at, and here it is 1 by a into sine 2 t into e raised minus 3t. That is by shifting theorem. Uh, Actually, what we are doing here is the inverse Laplace transform of 1 by s square plus uh, 2 square is sine 2t, and uh, e raised to minus 3t into sine 2t as the Laplace transform 1 by s minus minus 3, that is s plus 3 the whole square plus 2 square. So it is equal to 1 by 4 e raised to minus 3t into sine 2t. That is um, nothing but the Laplace transform of left hand side. Now uh, what we have here is 1 by 4 into e raised to minus 3t into sine 2t is f of t divided by t. So what we are looking for is an expression for f of t, and f of t is equal to uh, t e raised to minus 3t sine 2 into t divided by 4. So this is our required Laplace transform, inverse Laplace transform of the given function. Now let's solve another problem. Um, let's find the inverse Laplace transform of 3 divided by s minus 5 e raised to minus s divided by s square plus 4 e raised to minus 2s divided by s square. So this is equal to the inverse Laplace transform of 3 by s minus 5 into the inverse Laplace transform of e raised to minus s divided by s square, then plus 4 into inverse Laplace transform of e raised to minus 2s divided by s square. Now here at this point of time the parameter e raised to as come into picture when we use second shifting theorem, which says the Laplace transform of f of t minus a into u of t minus a, the unit step function, is equal to e raised to as into f of s. So that is where we have the first second shifting theorem, and at this step we have e raised to minus as come into the picture, and therefore uh, in our first case it is 3 into the Laplace transform of t Laplace transform of 1 is 1 by s, so it is 3 into 1 minus 5 times here 1 by s square is the L inverse of 1 by s square is t by uh, so, and okay, so it is t minus uh, here a is equal to 1, so it is t minus 1 into u of t minus 1. U of t minus 1 is a unit step function which takes value 0 up to the point 1 and is equal to 1 after 1. Then plus 4 times again 1 by s square is the Laplace transform of 1 by s square is the Laplace transform of t, so it is t minus 2 into u of t minus 2. So this is our required inverse Laplace transform. So this is equal to 3 minus 5 into t minus 1 into u of t minus 1 plus 4 into t minus 2 into u of t minus 2. So this is the function expressed using unit step functions, and this one can be written as a tabulated function f of t is equal to say, if you consider the real line, then it is 1, u of t is equal to 0 before the point 1, and u of t minus 2 is 0 up to the value 2. So if we have the value of t which is less than, if t is less than 1, then u of t minus 1 and t minus 2 are equal to 0, and we have the value 3. And if t is in between 1 and 2, the value of function is 3 minus 5 into t minus 1. And if t is greater than 2, then we have t 3 into 5 times t minus 1 plus 4 times t minus 2. So this is how we express the function as a tabulated function. Now another problem, let us find the inverse Laplace transform of tan inverse A by S. And this another case in which we take f of s is equal to tan inverse A by s, then df of s by ds is 1 by 1 plus A by s the whole square into derivative of A by s is minus A by s square is equal to minus A by s square into uh, 1 plus a square by s square. So what we have here is minus d by ds of f of s is equal to a by, if we take LCM here, it is s square plus a square divided by s square get cancelled. This s square in the denominator and this particular s square here will get cancelled, and it is a by s square plus a square. And now uh, if we take the Laplace transform, Laplace transform of a by s square plus a square is t into f of t. And this will give sin at is equal to t into f of t, and therefore in simple words f of t is equal to sin at divided by t. So we find the Laplace transform of tan of a function, tan of a by s is calculated. Tan of so the conclusion, L inverse of tan of a by s, L inverse of tan of a by s is equal to sin at divided by. So that's another method by which we calculate the inverse Laplace transform. Let's solve one more problem before we just winding up. L inverse of e raised to minus s divided by s plus 4 the whole cube. Here e raised to minus s is a result of our second shifting theorem, which gives the Laplace transform of f of t minus a into u of t minus a is equal to, this is equal to e raised to minus as into f of. Then the first shifting theorem says that Laplace transform of e raised at into f of t is equal to capital F of s minus a. as our first shifting theorem. We have to use both these results here, and the inverse is okay. Let us start with the L inverse of 1 by s plus 4 the whole, and this is equal to t raised to 2 uh, divided by 2 factorial into e raised minus 4t. So t square has Laplace transform of 2 factorial divided by s raised 2 plus 1, that is s cube. And in that s cube, s is replaced with s minus minus 4. So we have a parameter e raised to minus 4t. So that is due to the first shifting theorem. Now the required Laplace transform is obtained by using second shifting theorem. That is the required Laplace transform is uh, f of t minus a, that is t minus 1 the whole square into e raised to minus 4 into t minus 1 divided by 2 factorial is 2 into u of t minus 1. So that is using the second shifting theorem. Okay, we can express this uh, function as f of t is equal to 0 when t is less than 1 and is equal to t minus 1 the whole square into e raised to minus 4 into t minus 1 divided by 2 when t is greater than 1. So that's the required solution. So that is, I think that is enough for today in this session. And our next section, we are dealing with uh, convolution of functions and Laplace transforms. So the inspiration behind this is if you have two functions f and g, then we think about the Laplace transform of f plus g and the Laplace inverse transform of f of g and plus g of t. These two can be solved using the linear property or the property of linearity of Laplace transforms. But what about the Laplace transform of f into g or Laplace transform of f into g, the capital F into capital G? They are the Laplace transform of small f and small g. How we can relate uh, these two things? Or when we think about the Laplace transform of product of two functions, how we can find or how we can relate them. That is the inspiration behind the convolution theorem, and we'll discuss about convolution theorem in our next session. And for the time being, this is enough, and I recommend you to have a number of problems, work out a number of problems.